Hello, and welcome back to the Quantum Networking channel by Aliro Quantum. If you're joining us for the first time, I have some helpful resources to highlight for you. First, if you have questions during the presentation, please send those questions to us anytime through the Ask a Question box below. I'll monitor questions throughout our time together, and we'll answer as many of them as we can at the end of the presentation. You can download slides from today's presentation, as well as a quantum networking solution brief anytime by clicking on the Attachments tab below. We also have a white paper for you all about quantum memories available for download. Lastly, this webinar is being recorded and will be available to view on demand following today's live broadcast. I'm Emily Carter. I'm the Community Manager at Aliro Quantum, and today I'm joined by Daniel Winton, Solutions Engineer at Aliro Quantum. Today, we are looking at the basic building blocks of quantum networking and focusing on what you need to know about this technology to understand how it works at a high level, from the quantum physics that underpins quantum communication to the necessary components you'll find in a quantum network. Welcome to the Quantum Networking Live broadcast, Daniel, and thank you so much for being here today.
Hi, Emily. Thank you for the awesome introduction. I also want to thank everyone joining me here today live and in the future via the recording. I'm very excited about today's webinar, so let's jump into it. Since today's webinar is all about quantum networks, and really entanglement-based quantum networks, we'll start off by discussing what they are. From now on, if I say quantum network, please note that I'm referring to entanglement-based quantum networks. We'll then go into a very detailed example of a quantum network. Through this example, we'll see some of the protocols and hardware and software components that are employed by quantum networks, and the use cases and applications that are enabled by quantum networks. While this example will help show what quantum networks could actually look like at each layer of the stack, it will not and cannot capture what every single quantum network will look like. This is because there's a huge variety of quantum networks, both in terms of design and use cases, and with that variety comes incredible versatility. To conclude this webinar, we will touch on exactly those 2 points. Entanglement-based quantum networks can connect together quantum devices, such as quantum computers, quantum sensors, etc., by distributing entanglement between them. The distributed entanglement can be used to run amazing end-user applications, such as quantum circular communications, often referred to as QSC. It's important to note that entanglement-based quantum networks don't only exist in science fiction or in the future, but that there are already entanglement-based quantum networks up and running. Pictured here in the middle graphic is a schematic for the EPB quantum network, which is the first commercial quantum network in North America that launched this past year. To hear more about what is going on with the EPB quantum network and other quantum networks in North America and globally, you can check out an awesome webinar we recently put on called Real-World Quantum Network Deployments. Quantum bits, or qubits, are the quantum analog of classical bits. Just like classical bits are the basic unit of information that classical devices like your phone, your computer, and the internet are built upon, quantum bits are the basic unit of quantum information that quantum computers, quantum sensors, and quantum networks are built on. While classical bits and quantum bits are analogous in this way, they are actually quite different in behavior. Quantum bits have many quantum properties that classical bits do not. It is these properties of qubits that enable the quantum technologies that use them to outperform their classical counterparts. Qubits can be coupled together in such a way that measuring one qubit will affect the state of the other qubit or even other qubits. This type of coupling is known as entanglement, and we say that coupled qubits are entangled. Measuring one qubit will instantaneously affect the state of a qubit or the qubits it is entangled to, even if these qubits are many light years apart. This is exactly the spooky action at a distance that upset Einstein and many other physicists in the early 20th century. While measuring one qubit will affect the state of a qubit that it is entangled with faster than light can travel between them, it is important to note this does not mean we can use entanglement for faster than speed of light communication. That being said, use of entanglement in a network setting still has many incredible benefits. Entanglement is said to be distributed between two users on a quantum network if each user receives a qubit from an entangled pair. The distributed entanglement can be used by the users to achieve things like faster computing, more precise sensing, bolstered cybersecurity, etc. To explore quantum networks, we will start by working through a detailed example of a quantum network. In this example, we have two parties, Alice and Bob, who need to communicate top secret information. There are many types of information that need to remain secure, such as information related to defense and military, intellectual property, financial information, medical information, etc. Keeping information secure can be a matter of personal, organizational, and even national security. Alice and Bob have decided to use an entanglement-based quantum network to communicate their top secret information, as it is the only provably secure option. They will use entanglement-based key generation via the BBM92 protocol to secure their communications. It's important to note that there are many other entanglement-based applications beyond key generation that can be used to help secure communications. The family of all such applications are known as quantum secure communications, or QSC. Alice and Bob are located 200 kilometers apart. This means that they cannot use a single point-to-point connection for their quantum channel, as point-to-point connections typically only support links of up to 50 to 100 kilometers. However, through the use of 3 intermediary nodes in the form of quantum repeaters, evenly spaced between them, Alice and Bob will be able to utilize their quantum network and secure their communications. In our graphics, we will use a blue line to represent Alice and Bob's quantum channel and a red line to represent Alice and Bob's classical channel. We'll give a list of the hardware components employed by Alice and Bob's quantum network. Each of the 5 nodes contains entangled photon sources to produce entanglement on each individual node, quantum memories to store quantum information on the nodes, CNOT gates for an entanglement purification protocol, which we'll discuss later, Bell state measurement stations, and in this case, we'll be using probabilistic Bell state measurement stations, which are made up of single photon detectors and beam splitters. We'll be using these Bell state measurement stations for our elementary entanglement generation protocol and entanglement swapping protocol, which again, we'll discuss later. Alice and Bob's nodes will use quantum random number generators to provide true randomness for BBM92. Classical communication will be used in our quantum network protocols for things like heralding results, timing and synchronization, etc. It's important to note that quantum networks will not be used to completely replace classical networks, but instead will be used together with classical networks to enable performance in new applications that neither network can accomplish on its own. There are 2 important things to note about quantum network hardware. First, while repeaters, the intermediary nodes used to extend the distance of distributed entanglement, are not commercially available, the components that they consist of are. Second, hardware used by quantum networks can differ in types of components used and makes, models, and vendors of the components. Components will continue to evolve, and requirements for each network will differ, so there might never be a uniform set of components used for all quantum networks. The quantum network stack is the implementation of protocols needed to accomplish our 2 big quantum networking goals of distributing entanglement and then utilizing the distributed entanglement. The stack is typically broken into 5 layers. Starting from the bottom, the physical layer is used to attempt entanglement generation. The link layer is used for robust direct entanglement generation. The network layer is used for end-to-end entanglement distribution. The transport layer is used for qubit transmission. And finally, once we have accomplished the tasks of the first 4 layers, we can carry out end-user applications, which is the top layer of the stack. We'll examine what each layer of the stack entails by working through our example of entanglement-based key generation. While specifics of protocols used in the stack could differ, this example will still give a good overview of what a quantum network really is and does. We will start from the bottom layers. The first three are used to distribute entanglement and work our way up to our application of entanglement-based key generation. For our quantum network to be able to best meet the needs of its users and run their desired applications, there are several goals that our entanglement distribution needs to meet. We want for the distributed entanglement to have high quality. Quality of entanglement is usually measured in terms of fidelity, which measures how similarly the distributed entanglement we end up with is to the intended distributed entanglement. The closer we come to achieving our intended distributed entangled state, the better. We need the distributed entanglement to meet a certain level of fidelity in order to run our desired end-user applications. We want high throughput or message delivery rate for our entanglement distribution. Applications will often require many entangled pairs, and so we need to distribute enough entangled pairs to run them. We will sometimes want to connect distant quantum devices. For example, we might want provably secure communication, which again can only be achieved through entanglement-based quantum networks between two far-apart users. It's important to note that small-scale entanglement-based quantum networks will also be very useful. For example, clustered quantum computing will typically take place in a single warehouse, and there are times we'll need provably secure communication between two nearby users. In order to meet these goals, we need to appropriately choose hardware, software, protocols, and topology, make logistical decisions, integrate with existing classical systems, etc. While quantum networks share the same general goals of distributing entanglement and then utilizing the distributed entanglement, each user will have unique requirements. For example, users could want to run different applications, of which there are many, and could face different constraints, such as budget, logistics, etc. As you can see, there are many factors to consider when designing a quantum network. Use of a quantum network simulator with enough accuracy and capabilities to model, verify, and validate network designs is vital for making the design process efficient and effective. Similarly, a quantum network simulator will be useful for upgrading and scaling your quantum network as well. There are three main processes involved to meet our goals for distributing entanglement. Starting from the bottom of the graphic, elementary entanglement generation, EEG, which is used to distribute entanglement between nearby devices. Note that for local area quantum networks, we don't need repeaters or other scaling technologies. We could solely use EEG for entanglement distribution. Entanglement purification, sometimes known as entanglement distillation, which is used to ensure that the quality or the fidelity of the entanglement stays high enough throughout the entanglement distribution process so that we can use it for end-user applications. And entanglement swapping, which is used to extend the distance of the entanglement distributed by EEG. Using swapping and EEG together will allow us to distribute entanglement across far distances. These processes we just mentioned line up exactly with the bottom three layers of the quantum network stack. EEG is a physical layer protocol, entanglement purification is a link layer protocol, and entanglement swapping is a network layer protocol. We'll discuss each of these processes in more detail. We'll start with elementary entanglement generation. In EEG, we distribute entanglement between nearby quantum nodes. There are many protocols and even families of protocols for doing EEG. The example shown in the graphic here depicts a meet-in-the-middle scheme, which we will discuss in more detail in the next slide. Another common type of scheme is that of midpoint source, where an entangled pair is created at a single midpoint, and then each of these entangled qubits is transmitted to the two desired nearby nodes. For our example, we'll be using the meet in the middle technique shown in the graphic below. The first step is to generate an entangled pair consisting of at least one photonic qubit on each of the two neighboring nodes. We will use an entanglement source to do this. We then transmit A, or the, photonic qubit from each of the two entangled pairs to a probabilistic Bell state measurement station, which consists of a beam splitter and two single photon detectors via optical fiber. The two qubits must arrive at the Bell state measurement station at exactly the same time. We can use quantum memories to help ensure this is the case. Depending on which sides of the beam splitter the photons exit, and we can check this by checking the clicks of the photon detectors, we can tell if the entanglement generation was successful. If it was not, then we'll try again. This method has a 50% success rate. We next discuss entanglement purification. In entanglement purification, we use multiple entangled states with lower fidelity to create a single entangled state with higher fidelity. Purification protocols need a certain level of fidelity for each used entangled state, and so we need to make sure that fidelity has not degraded too much by the time we do purification. Qubits are fragile in the quality of their quantum information. In this case, the fidelity of the entanglement decays due to noise. Noise refers to many different factors that can cause loss of quantum information, such as environmental factors, manufacturing defects on components, natural physical processes, etc. To combat noise and keep fidelity at a high enough level so that we can even do purification, and eventually so that we can run end-user applications, we must use purification many times throughout the entanglement distribution process. Again, like with EEG, there are many different purification protocols that we can use. We will be using a controlled NOT or CNOT gate in our purification protocol, so we'll first introduce it here. CNOT gates are essential components of gate-based quantum computers. They are often used to entangle and disentangle quantum states in quantum computing algorithms. However, they can also be used in quantum networks, as we will see. CNOT gates operate on two qubits. The CNOT gate flips the target qubit if and only if the control qubit is a 1. The graphic below shows a few different representations of CNOT gates. It's important to note when it comes to optical components, so that is using photonic qubits and photonic systems, our CNOT gate will be probabilistic. We will use a relatively simple but still illustrative example of a purification protocol. Alice and Bob share two entangled pairs. Psi1 is the entangled pair whose fidelity they are trying to increase, and Psi2 is the entangled pair they are using to help accomplish this. Alice and Bob first apply CNOT gates on their two qubits respectively, with the control qubit being from Psi1 and the target qubit being from Psi2. Alice and Bob next measure their half of the pair of qubits from Psi2 and compare the results. If they get the same result, then the distillation is considered a success, and they will keep Psi1. The fidelity of Psi1 will be at least as high, but often higher than as before. If they get different results, then the distillation or purification is considered a failure, and they will discard Psi1 and try again. We will leave the math behind why this protocol works for another time. Finally, we discuss entanglement swapping. With entanglement swapping, we can essentially glue together two entangled pairs to create a longer distance entangled pair. In this graphic, we have two entangled pairs, and one qubit from each pair is on the same midpoint node. We measure the two middle qubits in a clever way, again doing a Bell state measurement, and when we do, the two further apart qubits will become entangled to one another. This process is actually pretty similar to the meet in the middle elementary entanglement generation scheme that we discussed. Using EEG and then swapping will allow us to distribute entanglement across far distances. Using purification will help ensure our fidelity is high. We'll run through an entanglement distribution example that utilizes these 3 repeater steps on Alice and Bob's network. We will be assuming that all of our probabilistic processes work on the first try in this example. Otherwise, this example could get a little bit too complex and lengthy. Our goal in this example is to distribute entanglement between Alice and Bob. The first thing we're going to do is perform EEG to get distributed entanglement between each pair of neighboring nodes. After running our EEG protocol for each pair of neighboring nodes, we'll have entanglement between Alice and repeater 1, between repeater 1 and repeater 2, and so on. We need to distribute entanglement between neighboring nodes before we can do entanglement swapping. Note that we might want to do multiple elementary entanglement generations between each pair of neighboring nodes so that we can perform entanglement purification. For example, we could perform elementary entanglement generation multiple times between Alice and repeater 1, and then use those multiple entangled pairs to create one higher quality entangled pair between Alice and repeater 1. When we go through the rest of this example, remember that we might want to do things multiple times in order to be able to purify our entanglement and ensure fidelity stays high enough so that Alice and Bob can actually make use of the distributed entanglement. We would also want to do this whole entanglement distribution process that's going to be shown in this example many times because Alice and Bob will want to use more than just one shared entangled pair. Now that we have entanglement between each pair of neighboring nodes, we're ready to do entanglement swapping. Here we'll perform a swap at repeater 1 to extend our entanglement from Alice to repeater 1 to Alice and repeater 2, which is closer to Bob. After the swap, we went from entanglement between Alice and repeater 1 and entanglement between repeater 1 and repeater 2 to having entanglement between Alice and repeater 2. Next, we'll perform a swap at repeater 3 to extend our entanglement from repeater 3 and Bob to Bob and repeater 2, which is closer to Alice. It's important to note that we could have done the 2 swaps we mentioned at the same time or in opposite order. After the swap, we went from entanglement between Bob and repeater 3 and entanglement between repeater 3 and repeater 2 to having entanglement between Bob and repeater 2. Now we perform a swap at repeater 2 to extend our entanglement and give us entanglement between Alice and Bob. After the swap, we have entanglement between Alice and Bob, which was our goal in this example. Like we mentioned earlier, we will likely want to do purification throughout this process many times to keep entanglement quality high, and we will also likely want to do this process many times so that Alice and Bob share multiple entangled pairs instead of just one shared entangled pair. This example was relatively simple. In more complicated networks, there will be many paths we can choose between end users instead of just one single path through which we can distribute our entanglement. We already discussed some of the hardware components and protocols needed to distribute entanglement, but what about software? Control and orchestration software is necessary to configure, manage, run, and actually use the networks. Even for very simple quantum networks with relatively few components, it's nearly impossible to manually configure and manage hardware for a singular experiment, yet alone for actual end-user applications. This software is needed to handle other important distribution-related tasks, such as retransmission and routing of information. With things like noise, loss, and probabilistic protocols, we will almost certainly need to retransmit information at multiple layers of the stack. While our network example was relatively simple, with only one path between Alice and Bob, there can be many paths we need to choose between. We will want to use software to select pathing to optimize for factors like security and throughput. As we discussed earlier, quantum networks will vary greatly in terms of hardware employed, and thus it's vital for the software to be hardware agnostic, since we don't want to create a whole software stack for each quantum network or every time a hardware component is upgraded or changed. We carry out, with appropriate choices of hardware and software, our three protocols of EEG, entanglement purification, and entanglement swapping, as we did in our 5-node example. We do this many times to distribute a sufficient amount of high-fidelity entanglement between Alice and Bob. Once we've done that, we are ready to start our key generation process. Remember that in our example, Alice and Bob are using distributed entanglement for the purposes of QSC and specifically for key generation to generate a key and help secure their top secret information. Before we jump into BBM92, we will talk about entanglement-based key generation more generally. Entanglement-based key generation utilizes distributed entanglement to generate a shared secret key between end users. This method has information theoretic security, which means regardless of how strong a computer you're using, whether classical or quantum, it cannot be broken. This is especially important considering the impending nature of Q-Day, which we have an amazing webinar dedicated to. Beyond just information theoretic security, entanglement-based key generation is also secure in implementation, as the key will never be revealed anywhere on the network. The shared secret key can be used in many ways by classical networks. We will give several such examples in a later slide, but in our example, Alice and Bob will use their shared secret key via a symmetric encryption algorithm, such as AES-256, to encrypt and decrypt messages and thus secure their communication. In this graphic, we have Alice and Bob with their classical and quantum channels. The key is generated using the quantum channel with help from the classical channel, and we'll see what this key generation actually looks like when we go through BBM92. The key is then used by the classical channel to help secure Alice and Bob's classical communications. BBM92 is the canonical entanglement-based key generation protocol along with E91. It was developed in 1992, and its security has withstood the test of time. However, it just recently started to be implemented as quantum network technology has developed. There's 6 main steps: basis selection, measurement, conversion to bits, sifting, calculating qubit error rate, and generating the final key. This graphic actually contains an example of generating a key via BBM92. We will revisit this example after we discuss each step in more detail. Measurement bases are ways to view and measure qubits. Alice and Bob choose a measurement basis for each of their qubits from the distributed entangled pairs. Choice of each measurement basis is chosen independently and randomly. We will use quantum random number generators for this process to ensure true randomness. We will use the canonical choices for bases of the Z basis, which has possible measurement results in terms of 0 and 1, and the X basis, which has possible measurement results in terms of plus and minus. These bases coincide with the Z-axis and the X-axis of the block sphere representation of qubits, respectively. As an analogy to help visualize these bases, imagine we have a collection of blocks. They can be at any angle. The Z basis views the blocks in terms of being at a completely vertical or completely horizontal angle. When we measure the angle of a block in the Z basis, we must get one of these two angles. The X basis views the blocks in terms of being tilted 45 degrees left of vertical or tilted 45 degrees right of vertical. When we measure the angle of a block in the X basis, we must get one of these two angles. The probability for which basis state we will get upon measurement depends on how close the angle of the block is to the angle of the basis state. For example, a block that's mostly vertical will be more likely to be measured in the z-basis as vertical than horizontal. With different measurement bases, we are still looking at and measuring the same qubits, but through different lenses. Alice and Bob measure each received qubit in the selected basis. The measurement process collapses the quantum bits quantum state, a superposition of multiple states, into exactly one of the basis states. Note that in every protocol we have discussed today, we have made measurements. For example, with Bell state measurement stations in our EEG protocol and in entanglement swapping, and measuring the target qubit in our purification protocol. Our measurements have been carried out, at least in part, by single photon detectors. If Alice and Bob measure their qubit in the same basis, then they will get the same result. For example, if they both measure in the z basis and Alice gets result 0, then Bob must also get result 0. Similarly, if they both measure in the x basis and Alice gets result minus, then Bob must also get result minus. However, if Alice and Bob measure in different bases, then we can have any combination of measurement results. For example, if Alice measures in the z basis and Bob measures in the x basis, we can have results 0 and plus, 0 and minus, 1 and plus, and 1 and minus. Alice and Bob convert all of their measurement results from quantum states into bits, that is, into zeros and ones. When measuring in the z basis, the measurement results are already in bits. When measuring in the x basis, we're going to convert plus to 0 and minus to 1. Assuming that there's no noise, if Alice and Bob measure a qubit in the same basis, then they will always receive the same bit value. If Alice and Bob measure in different bases, then there's a 50% chance that they will receive different bit values. This is because there's a 50% chance of getting measurement results 0 and minus, or 1 and plus, or vice versa, which yield different bit values. There's also a 50% chance that they will receive the same bit values. This is because there's a 50% chance of getting measurement results 0 and plus, or 1 and minus, or vice versa, which yield the same bit values. The relationship between bases selected and matching of bits is going to be very important for the security of this protocol. To do the process of sifting, Alice and Bob share their choices of measurement bases over a public, authenticated classical channel and discard all results in which they use different measurement bases. The resulting bits are considered sifted. In the absence of noise or an eavesdropper, this means that Alice and Bob should agree on all remaining bit values, as they will agree on all measurement bases for these bits. Alice and Bob choose a sample of the remaining sifted results and compare them to estimate quantum bit error rate, or QBER. There's a trade-off here between taking a larger sample to get a better estimate and taking a smaller sample and having more bits to be used for key material. Alice and Bob are estimating the percentage of mismatched bit pairs out of the sifted material. In the perfect case, so in the case with no noise or no eavesdropper, the qubit error rate should be 0% because all of Alice and Bob's sifted measurement results must agree. Assuming no noise, if the qubit error rate is greater than 0, then we know with 100% certainty that an eavesdropper is present. An eavesdropper has to choose a measurement basis when measuring one of Alice and Bob's qubits. However, Alice and Bob's choice of measurement bases are not sent over the network until after their measurement occurs. This means that Eve will not have the ability to intercept that information prior to her measurement and thus could choose a different measurement basis than Alice and Bob. If Alice and Bob agree on measurement basis, but Eve measures her intercepted qubit in a different basis, then there's going to be a 50% chance that Alice and Bob will receive different bit values, leading to a non-zero qubit error rate. This is depicted in the graphic on the following slide of how an eavesdropper can contribute to qubit error rate. With noise present, qubit error rate will almost certainly be greater than 0. We attribute the qubit error rate completely to a potential attacker. As we just discussed, if Eve wanted to get any information about the key material, she would have to measure the system in some way. Because of quantum mechanics, the mere act of measuring disturbs the system and produces observable and detectable anomalies. All such anomalies contribute to the qubit error rate, but neither Alice nor Bob can distinguish whether they came from environmental noise or errors or an eavesdropper. The BBM92 protocol tolerates up to 11% qubit error rate, which corresponds to a fidelity of 89%. However, there's a trade-off between security confidence and throughput, so the exact value will differ based on individual user requirements. If qubit error rate exceeds the user's decided tolerance limit, the protocol determines that too much information was leaked to a potential eavesdropper, the generated key is discarded, and a new one is generated, typically on a different quantum channel. The graphic below shows how an eavesdropper could contribute to qubit error rate. Alice and Bob used the remaining bits that were not used in the sample used to estimate qubit error rate to generate a final key. While we could simply use the remaining bits as the final generated key, we will typically perform classical post-processing techniques such as information reconciliation and privacy amplification protocols on the remaining bits in order to generate a more secure final key. These classical post-processing techniques will be discussed in more detail in a webinar coming up soon. We will quickly go through the example shown in the graphic below. In this example, there's no noise and there's no eavesdropper. In reality, we'll have to deal with noise and potentially maybe even have to deal with an eavesdropper. There are also only 9 entangled pairs. In practice, we will need way more than 9 entangled pairs. For example, if we want to generate a key to be used in AES 256, we need a key of length 256 bits. This means we need more than 256 entangled pairs, as we lose bits to sifting and when sampling to estimate qubit error rate. Enough background, let's jump into this example. So we're going to start at the second row, which is the first step of BBM92, and then work our way down through each of the steps. First, Alice and Bob use their quantum random number generators to select a measurement basis for each qubit that they received. We see that for the first pair, Alice and Bob got the X basis and Z basis respectively. For the second pair, they both got the X basis, and so on. Next, Alice and Bob measure their qubits in the selected bases. Remember that when Alice and Bob have the same measurement basis, and there's no noise or eavesdropper, they will agree on measurement results. When Alice and Bob use different measurement bases, there's only a 50% chance that they will agree on measurement results. For the first pair, Alice and Bob got plus and 1, respectively. For the second pair, Alice and Bob both got minus, and so on. Alice and Bob then convert their measurement results to bits, with plus becoming 0 and minus becoming 1. Remember that when Alice and Bob have the same measurement basis, and there's no noise and no eavesdropper, they will agree on bit values. When converting to bits, we get 0 and 1, 1 and 1, and so on. Next, Alice and Bob do sifting. They share their choices of measurement bases over a public, authenticated classical channel and keep the bits in which they use the same measurement basis and throw away the bits in which they use different measurement bases. For the first pair of bits, Alice used the X basis and Bob used the Z basis, and so they throw away those bits. For the second pair of bits, Alice and Bob both use the X basis, and so they'll keep these bits. They continue this process for all 9 pairs of bits. Now, Alice and Bob use a sample of the remaining bits to estimate qubit error rate. They choose the second and fifth pair as their sample. They find that the bit values agree for both pairs, and so qubit error rate is estimated to be 0% and fidelity to be 100%. Finally, Alice and Bob use the remaining bits as their generated final key. They have generated the key 101. In this example, we didn't do any classical post-processing. In practice, we would typically use post-processing techniques such as information reconciliation and privacy amplification. Notice that in our example, we use 9 entangled pairs to generate a key of length 3 bits. While this is not an exact ratio for entangled pairs to resulting bits left for key material, this example still gives an idea of what one might expect for that ratio. A shared secret key can be used in many ways by a classical network. In our example, Alice and Bob generated their key to be used by a symmetric encryption algorithm in order to encrypt and decrypt classical messages. Shared secret keys can be used for other things beyond encryption and decryption, such as for passwords, generating new keys using a key derivation function, identity authentication via challenge response protocols, message authentication via message authentication codes, etc. You might have noticed that we covered the 3 bottom layers of the stack when discussing EEG, purification, and swapping. We then jumped to the application layer with BBM92, skipping past the transport layer. The transport layer was not utilized in this example. This doesn't mean the transport layer is not important. It's incredibly useful for many applications. We'll get into that more in the next slide, where we discuss the transport layer protocol of quantum teleportation. Quantum teleportation is an entanglement-based protocol, and sometimes even considered an application, that utilizes distributed entanglement to communicate quantum information across the network. This is illustrated in the graphic below. Alice and Bob share an entangled pair, and Alice has a qubit that she wants to send to Bob. By consuming the entanglement, Alice can send the qubit to Bob. The entangled pair has to be measured during this process, essentially collapsing the qubits into classical bits, and so it can't be reused in this way. We have an awesome webinar that's available on demand, explaining in detail how quantum teleportation works. Quantum teleportation is a transport layer protocol. Many distributed quantum applications require communication of quantum information between devices. Teleportation is the protocol we would use to do just this. The way in which information is sent via teleportation also has useful properties for cybersecurity purposes. You can use quantum teleportation to communicate quantum information to endpoints on the network without that information ever being exposed on the network itself. This means that even if intermediary nodes between communicating users become compromised, the quantum information that is being sent between them will not be. In this way, the security of quantum information being sent is said to be device independent. The quantum network in our example had a linear topology. That is, there was only one path between the 2 end users. It was 200 kilometers long. It employed hardware, software, and protocols to carry out its specific goal, which was to be used for QSC and specifically for BBM92 key generation. This example does not come close to encompassing all quantum networks. Quantum networks can vary in many important ways, such as topology, size, components, protocols, use cases, applications, etc. And we've seen this a few times during this webinar. For example, local area, metro area, and wide area quantum networks, different protocols such as meet-in-the-middle schemes versus midpoint source schemes for EEG, differences in hardware components, etc. Part of the reason quantum networks vary so much is that they can be used for so many things. That's not to say the same entanglement-based network can't be used for multiple use cases. It definitely can, and that's actually one of the great features of entanglement-based quantum networks. However, a quantum network that connects together quantum computers in a warehouse versus a quantum network that connects quantum devices together across the globe for a multitude of use cases will most likely differ in multiple ways. Three of the main use cases of entanglement-based quantum networks are quantum secure communications, distributed quantum computing, and distributed quantum sensing. Many amazing applications of these use cases are known and are being used today, and many more will be developed as we progress to the global scale quantum internet. We'll give a quick overview of each of these three use cases. Quantum secure communications is the family of security solutions that are enabled by entanglement-based quantum networks. We already saw that entanglement-based key generation and quantum teleportation allow us additional security when communicating information. We can also use entanglement-based quantum networks to directly communicate classical and/or quantum information in a provably secure manner, to detect eavesdroppers of classical and/or quantum information, etc. Distributed quantum computing is the connection of multiple quantum computers. In entanglement-based quantum networks, these computers are connected by distributed entanglement. These computers can be close together or far apart. By connecting the computers together, we can achieve much greater computing power and additional security than individual quantum computers and networked or individual classical computers can achieve. Distributed quantum sensing is the connection of multiple quantum sensors. In entanglement-based networks, these sensors are connected by distributed entanglement. These sensors can be close together or far apart. By connecting the sensors together, we can achieve much greater accuracy, sensitivity, and precision than individual quantum sensors and individual or networked classical sensors can achieve. In this webinar, we went through a detailed example of what a quantum network looks like and one such application it can run. We also saw the huge variety and versatility of quantum networks. If any of these entanglement-based use cases and applications that I touched on today sound potentially useful to you or your organization, please feel free to reach out to us at the email listed on this slide. We love talking about all things quantum networks and would be more than happy to provide any additional information and to find a solution that works best for you. I'm going to spend our remaining time together answering any questions that came in today during the webinar.
Excellent. Daniel, thank you so much for this presentation. Quantum networking is a complex technology, and it's really great to be able to unpack it from these various angles that you did for us today. And we do have some really great questions for you. Folks, if you have questions, please add them to the queue. If there are any questions that we can't get to during the time that we have today, we will follow up with you individually after the session via email. Danny, our first question is asking, is this the same as QKD, quantum key distribution?
Okay, this is a great question. So I guess we'll first start off by saying what QKD is. So QKD typically refers to QKD networks or prepare and measure systems and networks that have been around for almost 3 decades now, or around 3 decades now. The more recently available and more recently deployed entanglement-based networks differ from QKD networks in several important ways. So, as their name suggests, QKD networks are used for QKD. They're single purpose, they're used for quantum key distribution. Entanglement-based networks can be used for multiple things. And we touched on this briefly during today's webinar, so they can be used for distributed quantum computing, distributed quantum sensing, quantum secure communications, which includes key generation but extends beyond just key generation. So, like I mentioned, QKD networks are prepare and measure based networks. They're not entanglement based. So if Alice and Bob are communicating, Alice will prepare a quantum state and then send it to Bob, who will measure it. They're not operating by distributing entanglement and then using that. And the way QKD networks work when they want to extend the distance of the quantum information they're transmitting is they use trusted relay nodes. And this name's a little bit misleading. So these aren't relay nodes that we can trust. They're relay nodes that we need to trust. And that's because if they become compromised, the information that we're sending over these prepare and measure networks will also become compromised. Entanglement-based networks use repeaters, and we talked about this today. They're used to extend the distance of our distributed entanglement instead of relay nodes. And they don't have the same security vulnerability. We touched on this a bit when we talked about teleportation. When we're communicating information on our entanglement-based network, that information is never present on the network itself. So even if one of these repeaters becomes compromised, the information we're transmitting won't become compromised. So I think that gives a good high-level difference of QKD networks versus entanglement-based networks. As an aside, a fun fact is that we talked about BBM92 a lot during today's webinar. It is often considered the entanglement-based version or analog of BB84, which is the canonical QKD algorithm. And even though it's the analog of this QKD algorithm, it addresses several of the vulnerabilities that come with BB84, such as the one we just mentioned with the trusted relay nodes. And you might notice we have BBM92, BB84. They both start with BB. That's because the BB portion of their names comes from their creators, Bennett and Broussard.
Excellent. Danny, thank you so much for that. Really excellent explanation. Very important differences between these two types of networks. Our next question is focusing on hardware, specifically on repeaters. So how are quantum repeaters different from classical repeaters? Why can't we use classical repeaters and routers for quantum communication if we're using photons? It's a great question.
Yeah, so we're using photons and we're using optical fiber, which is infrastructure that already exists. So that's a natural question of why don't we just use classical repeaters too? And this is for a few reasons. So there are a few reasons why we can't use classical repeaters for quantum networks. So first, the way classical repeaters typically work is they copy and they amplify our classical signals. But this is impossible for quantum information, and that's due to a very famous principle, or a very famous principle captured by the no cloning theorem. And what the no cloning theorem tells us is that it's impossible to create an identical copy of an arbitrary quantum state. So we can't use this process classical repeaters use of copying and amplifying classical signals because we can't create identical copies of arbitrary quantum states. Classical repeaters are designed for classical information processing. They're not designed for quantum information processing. So, for example, they can't store quantum photons. They can't carry out the protocols we need to combat decoherence, which we talked about. It's the degradation of our quantum information from noise and other factors. And they can't help us maintain the often fragile quantum information that we intend to transmit. So there's several reasons we can't. I'm sure there are other reasons too, but that should give a decent understanding of why we can't use them in this way.
Yeah, thank you so much for that explanation. Our next question is about maybe organizations who are exploring this technology. What do organizations tend to misunderstand when they begin exploring quantum networking?
Okay. So I've engaged with a decent number of our clients, and we always talk about entanglement-based quantum networks. And I've seen a few common misunderstandings when it comes to this topic. So, one of the common misunderstandings is that quantum networks are going to completely replace classical networks. And this isn't the case. So, quantum networks are going to be used together with classical networks. And we saw how that might work with BBM 92. There were processes that take place on the quantum channel, processes that take place on the classical channel to do this process of key generation. And beyond that, implementation of quantum networks isn't going to require a massive overhaul or the obsolescence of classical systems. Another common misunderstanding is that I've seen multiple clients underestimate the technology readiness level of quantum networks. So quantum networks aren't a futuristic technology that are many years away from being able to be deployed. They're actually something that's ready for deployment today. And we did a good job capturing many of the projects going on in North America and globally in our real world quantum network deployments webinar. So if you want to see some of those deployments, that's a good place to look. Another misunderstanding I've seen is so there was underestimating technology readiness level, and there's overestimating that level of effort and the timeline of deploying your quantum network. So, for example, I've seen projects go from zero, like not even having requirements gathered, to having a local area quantum network up and running and equipped with quantum secure communications in under a year. And the last one I'll touch on, and I'm sure there's several more, but last one I'll touch on for time purposes, is that these quantum networks, these entanglement-based quantum networks, are single purpose. So you build your network, you can do one thing. But entanglement-based quantum networks and an individual entanglement-based quantum network can be used for many things. And again, we touched on this a bit with the use cases of distributed quantum computing, distributed quantum sensing, quantum secure communications. But within each of these use cases, there are many, many applications.
Excellent. So important to begin, as you said, starting your quantum networking journey now, so that you can figure out as an organization where are the gaps in your understanding, what can you actually begin doing much more quickly than maybe you think. I think we have time for just one more question today, and this one is about photons. Do we have to use single photons?
Okay, so when we went through our example, we used photons as our network qubits. We mentioned in many webinars, the qubits employed by quantum networks will be photonic ones. And so it makes sense that this question was asked, do we have to use photonic qubits as our network qubits? And I'm going to say I'm not sure that we have to use photonic qubits, but there are several reasons why we almost always do use photonic qubits. So they're compatible with existing infrastructure, such as optical fiber. They travel very fast. They travel at the speed of light. And this speed is helpful when we're carrying out our desired applications. Photonic qubits interact less with the environment than other types of qubits. And with that, they decohere less than other types of qubits. And beyond that, they can be used to connect together devices that use different quantum materials and systems. So photonic qubits are a good choice for connecting together different quantum computing platforms, for example, because for example, I've seen distributed quantum computing setups that connect together superconducting qubit-based computers with trapped ion-based quantum computers, and photonic qubits are effective at connecting together these types of qubits, and that's true for other types of qubits as well. So that's just a few. Again, there are probably more I'm missing, but I think we're out of time.
Danny, thank you so much. We are unfortunately out of time today. For folks who've asked questions that we didn't get to today, we'll reach out to you directly with answers to those questions via email. And if you have questions while you're watching the on-demand replay, you can direct those to info@aliroquantum.com. Thank you everyone for attending our podcast today. And Daniel, thank you so much for explaining the basics of quantum networking.